Greetings. This is part 2 of our repair adventure of the Peavey Midi streamer rack mount device. I think we made a lot of headway in part 1 because we brought it back from total death to near full functionality. But what remains is checking out the Midi communications hardware. What we have on the back, we have two Midi ins, 1 and 2. We have a Midi through, which is essentially hardwired to in 1, which means whatever comes in here is directly connected to this. It's a pass-through port. And then of course we have our general Midi output. Now the reason that we do have two UARTs, one here and one here, is that for every one of the inputs we do need a UART. And what this box offers in functionality is that you can have it merge input 1 and input 2 to create a single Midi stream that comes out of the output. So the second UART, this one, is only there to receive Midi input. It never transmits anything. But as we saw before, well, let's have a closer look at where things are located physically. So the Midi signals come in, and like in all Midi devices, they go through an opto-isolator, which is part of the Midi spec, you know. If you plug in anything that outputs nasty voltage, these will blow up and not the rest of anything else. It's a current loop, very similar to how teletypes were driven. And anyway, this basically converts the incoming current to voltage. It's a 5-volt current loop, and sends the communication, the digital signal, up to the UART, and the UART interrupts the CPU, and the CPU reads it, and that's how things get in. And when the CPU wants to talk back, it just sends out Midi commands which come out of the output over here. So I did a preliminary test, and if you remember, call me a pessimist, I said there's a chance that this may not work out of the box, and I wasn't a pessimist, I was right. And it wasn't easy to predict. It was easy to predict, I mean, because the signal comes in here, goes into the opto, and then flows all the way over here. I forget which is the first one, but it goes to one of these two. But again, remember, this is ground zero over here, and something must flow through here, because when I input Midi to it, I could see that it was getting to the opto, but and it was coming out, but it never made it over here. So obvious, this mess here has cut the line. On this board, it's kind of difficult to trace or to physically follow the traces that go from one pin to another, because obviously the lines meander all over the place, and they meander up and down through vias. And a lot of the vias are hidden by the actual chips. So, and the chips, the sockets they use, especially the smaller sockets, they're closed. They have a small gap in the middle. Well, these have a bigger gap. They're easier to see, but the little sockets don't. And it's kind of hard to trace it out. So my criteria are, I measure from, if this pin is supposed to be connected to this pin, I simply do a continuity check. If there is no continuity, then the trace got eaten somewhere, and I run a wire. So after doing comprehensive tests, and this is what we're looking at now, mostly the older repairs, but I did find this is the backside of the Opto, and this over here is a resistor, is a pull-up resistor that brings the output of the UART into the range of 5 volts, between 0 and 5 volts, and then feeds the UART. And that line, somewhere in this area, got eaten. So I made the connection, and it seems as if I saw some life out of it, but let's put it back together and actually get a device that makes a Midi sysx dump, i.e. it dumps some data, see if this can receive it, save it to disk, and then we can reverse the whole thing, i.e. load in the file we just received and saved, and see if we can send it back to the device that originally sent it, and see if that whole process works. I also started to look through my stock of power supplies to see if I had a 16 volt AC power supply, which I don't. 16, I guess 16 in general is a bit of an oddball number. 12s are, I did have a 12, and after looking at the specs for the swishing regulator over here, since it's only generating 5 volts, it looked like 12 volts should be enough. So I'm going to put things back together power-wise here, see if it still boots up, and then we can proceed to the Midi test. Alright, we're set up, and our test subject, well, first of all, I wired in the 12 volt supply. Let's see if that's enough to power it up. And it is. Second thing is we're going to use this to do a Midi dump and then receive that dump back and see if we can dump it, save it, restore it, and see if it gets sent back. Okay, first for a short data dump, what we're going to do is currently on the navigator is on preset 0, so we put it into the load dump section, and this SO, the wonderful UI interface, tells us that it is now ready to send one preset, and we were on preset 0, so what this is going to do is send preset 0 out the Midi port. Now we got to go in and tell it, we go to sysx, record, remote sysx receive, press start, and it's sitting there waiting for data to come out. So all we got to do here is press enter, and it's blinking the go, saying hit the enter key again and I'll send the data over. So goes, as I said, it was a short one, 776 bytes. Now it's asking us for a file name, and that is, it's wonderful to enter names with these 4 buttons. So we're going to keep it short. We'll call it let's call it AA. And then we hit start, and what it'll do, so this is the main function of this box. I mean, it has all the other functions, but it is to send system exclusive messages from a Midi device, which are basically data blocks, over to here, and then this saves it on disk. And then you take out your disk and you have your disk library with the presets and everything saved for whatever Midi device you're playing with. So now what we're going to do is turn things off, this one and this one. Then we're going to turn it on again. just to make sure that everything is at the beginning. And now we go back to system exclusive, but we press the transmit button. What it's going to do is read the disk. Well, it was frisking the disk. Anyway, so we have the file we called AA on here. And what we'll do is we'll read it and then pay attention to this display because it'll indicate that it's downloading, and then change again to basically tell us that it happened. You don't have to initiate a Midi receive on the navigator. It's open. It's listening for sysx messages all the time. So load the sysx file, start, and now press start to send it. That was pretty quick. It went to LD, meaning load, and then RC, received, which means I got it all right. So all of that worked, but that was rather short. So let's do something a little bit bigger. So now what we're going to do, what was it, like 700-800 bytes? Now we're going to send a larger amount of data. And the way that works is we go back to the load dump, and we're still on send 1. Send general parameters, and SA is send all. And that's close to 32K bytes. But one thing, if you know about Midi, is it only sends nibbles because it uses the highest bit as a status bit. So it's going to send something closer to 64K when I tell it to send to do a send all. So again, we got to go into record, start, it's waiting, and then on the navigator we say enter, it's going to say go, and it's going to start dumping data. Now that's going to take a little bit of time. As I said, it's going to be close to 64 bytes, even though this is only sending 30, well, it is processing 32 bytes, but again, it's breaking them up into upper-lower nibbles, so that's why we're getting close to 64. Boom, it's done. It sent all of the data. So now let's change this. We got to change the file name because it won't even let you overwrite files. You have to actually go in, manually delete files if you want to use the same file name. So we're going to call this one AB. And you can hear it. It used, what, 4 or 5 tracks for that. File save complete. We're done. Again, we're going to turn it off. No, power switch is in front. We're going to turn this guy off. It's always a good idea to do when you're making dumps and loads, because remember, this has an 80C31 in it, and if this is blasting out, almost 64K of Midi, the Oberheims are kind of famous for getting confused on receive. But let's hope that that famousness doesn't come out right now, because all we got to do, remember this, the navigator doesn't have to be set up to receive, it's always ready to. What we need to do here is go to System Exclusive Transmit. AA is not the one we want AB. Alright, so we start it. First thing it does is it reads it from disk, and then it says let me send it. So this immediately switched to load, which means it is receiving, and it's counting down the number of bytes over here. And once that's done, then it's basically going to tell us that this works, because we made a round trip, and boom, RC receives. This says it's done sending, and this says is that it received the data and that it checksummed it. And basically this doesn't look inside the packet it receives. A system exclusive starts with a hex byte F0 and ends with a hex byte F8. That's all this knows. When it sees an FO, it starts receiving. When it sees an F8, it stops receiving and writes it out to here. And this, when receiving, will get the F0, and it actually contains ID information. Is it meant for this device? And if all that passes, it starts processing the data. So this is actually doing a lot when it's receiving, and this is just blasting them out the front door. So we're done. This thing seems to be fixed. I'm going to put it in my setup and use it to just test it. And yes, I know it's a lot easier to just use a computer with a MIDI interface to do this kind of stuff, but this is artifact electronics, and I think this here is a true artifact. But anyway, as far as the procedure we went through, when you get something like this, the very first thing to do, regardless of how bad everything looks, is pull the EPROMs. Because yes, there are a lot of EPROMs available, EPROM images available, but never the one that you need immediately. Now you need to test these, and it's kind of difficult if you don't have anything to compare them to. How do you know that they work? You'll never know 100%, but there are a few things you can do. You take them and you read them. Stare at the binary dump of what you just read, and well, if it's all FFs, yeah, you just lost because the EPROM is dead. Now if you actually get data, you'll mostly get random bytes, and that's generally good. If you're lucky, you will actually get readable ASCII text, copyright notices, or text that gets dumped on the screen. And if you see that, then you know that you have a really good chance that you got a good EPROM. The other thing to do after that, whether you get readable text or not, is to do several subsequent reads of this on your EPROM reader, and kind of stare at the binary dumps you're getting and see if they're changing. On an intermittent EPROM, what will happen is it will return, you will still get random bytes coming out of it, but the patterns will change on subsequent reads, which, you know, obviously points to a defect in the EPROM. If that happens, the EPROM's dead, and you have no way of recovering your data. However, if you do several reads and it looks, I mean, the official way, of course, is to write a routine that takes subsequent binary dumps and does a compare on them. But if you don't have it handy, I found that just staring at the binary dumps after several reads, your eye can detect it if numbers are changing when they shouldn't be. When the pattern on the screen, which is the binary dump, changes, then you know you got a problem with the EPROM. I got lucky because the EPROMs were good. I used the procedure I just described, and that procedure seemed to tell me that everything's okay, and as it turns out, they were okay. And I have a secure copy of them on my machine. My second words of wisdom, or stupidity, depending on how you look at it, is I've fixed many boards with battery leakage damage, especially on pinball machines, because the early digital pinball machines all had NiCad rechargeables, and on those it was a little worse than here because the boards were mounted vertically, and if the battery leaked, you had the trickle-down effect because all of the leakage would leak down on the board depending on where the battery was, and wreak havoc in its path. This one kind of localized because I guess it was stored flat, So ground zero is essentially where you see this battery on this one. However, the problem I found is it's an iffy repair. I can't trust this guy for the following reason. Some of the traces were discontinuous or were broken somewhere in the middle, and some weren't. And the ones that weren't are the danger. Let me explain that, because I did clean this and the other side up significantly with vinegar and subsequently with alcohol, but I didn't get everything. There's still some nasty looking traces on here. You can see this one, for instance, here. And I could not clean them up. I could have scraped them a little more, but there was just too many of them. And what happens is, once you apply electricity, current flows into these again, and there is battery leakage in them, the corrosion will continue. Now, as I said before, if we have a trace that is broken somewhere in the middle that we've bypassed, we're okay, because the corroded part of that trace never gets to carry any current. It's interrupted, right? All the current flows through the new wire you put in. But the danger comes in on the traces that were not broken, that still conduct, because once you turn this back on, those traces are going to carry current. And if they still contain battery leakage fluid in them, that's going to wake them up, and the corrosion is going to march on. And after several weeks or months of happy usage, your device isn't going to work anymore. And the reason for that is that current passing through traces or connections that still have battery leakage on them will eventually corrode to the point where they break apart. I did change, I also see that in chips, because you can't, there'll be no corrosion on the legs or anything, but if the corrosion propagated through the leg and then hit the wire inside that binds the pin to the substrate, it'll eat that wire lickety-split, because the wire is really, really thin, and things won't work. The only thing you can do there is take out any sockets that have corrosion close to them, even if the socket looks clean, replace the socket and put in a new chip. And that's about the best you can do to prevent things. But don't fool yourself. Especially also on musical instruments, I've seen it where I fixed something and after 6 months it took a dump again. So that's an unfortunate fact, but hey, I did what I could and it works. And we'll just have to wait and see how long it lasts. Well, thanks for coming along on a ride to see how to fix something like this. And yes, it's a noble effort, because it isn't worth a whole lot, neither monetarily nor functionally, but I like to fix things. So please like, subscribe, do backwards somersaults and all that good stuff, and we'll see you next time.